Hello and welcome back. I'm Matthew, and this is part 3 of our series on installing MVS 3.8 under the Hercules emulator using Jay Mosley's instructions. So in our previous steps, we have prepared some of the preliminaries and created our environment on our Debian Linux system. In step 2, we copied the data from the starter system tapes to our DASD, to our emulated hard drive files on our mainframe. So now in part 3, we will be following the steps to use SMP4 to build the distribution libraries. So essentially, this will be copying the data off of the distribution tape, the actual MVS 3.8 installation media, if you want to think of it that way, into some staging areas on hard drives, DASD, on our emulated mainframe. SMP4 is the program, system modification program, that IBM provides to manage software installations and patching and other modifications in the MVS operating system environment. So let's dive in. You can see prerequisites. If we've been following along so far, we should have all of these completed already. We're going to be using the SMP4B tape. So this is a newer version of SMP that's needed to successfully install MVS 3.8. And then the product tape contains the actual product elements to build the distribution libraries that we will ultimately be installing MVS from. We have the scripts. We're going to use a lot of JCL scripts, and we're also going to receive additional patches, the program temporary fixes, as well as, very importantly, the community effort led by Jim Morrison, who put together these modifications to bring newer DASD support to the MVS 3.8 operating system. So at the time, the 3375, 3380, and 3390 hard drive types did not exist when MVS 3.8 first came out. But they're nice because they allow us to use bigger virtual drive images, and Jim Morrison managed to patch that support into the MVS 3.8 operating system. So pretty cool that we'll be able to do that and then use modern DASD types in our emulated mainframe system. All right, so we have some timing estimates as to how long this should take. We'll see. The first step is we need to create more hard drives, more DASD. In this case, we need to create them for the distribution library. We can use our create script again. So let's go back to our terminal window and do that. Create the dlib DASDs. Okay, so it looks like it created 3 new 3350 volumes for us. Work 00, work 01, and then SMP 00. So these work volumes will continue to be our work volumes on our final mainframe system. SMP will be the work area for that system modification program. So we won't tend to use that DASD for our own data, but it will still stick around and it will be used as we're applying system modifications, and it'll contain the distribution libraries for our system. You can see the commands that script ran if you want to do it manually. Remember, we had modified the script, so we're also using the -Z option to create compressed DASD images. You can read about this condition code script here. We will be using that after every step to make sure things worked correctly and that we don't encounter any unexpected errors. We'll be using the Perl version of it. You'll remember we set that up in part 1 video as some of our preliminary setup. So you'll see more of that as we encounter it. Now here Jay describes why we need to replace SMP on the starter system tape with the newer version, and then we'll walk through that process. So we are going to start up our starter system mainframe. You can see we have a printer this time. We have our card reader and a card punch. We'll still be interacting with a 3215 console. And we are going to be using one tape drive, and we'll have those couple of disk images that we already created for the starter system. All right, so we are going to start Hercules up with the SMP1 configuration file. So let's go do that now. Hercules-f conf smp1.conf. I still have this name 1052 console. I guess we can change that to be super accurate to our 3215 console. So still a line-oriented device. We're not using a full screen 3270 console yet, but this is what is in the starter system, so we can name that, what did we say, 3215? My memory is going on me. Yeah, 3215. Okay. So back to Hercules. So we started up Hercules, and we now have our mainframe with the hardware configuration shown here. And again, we need to connect to this 3215 console device. So that will be a telnet session. So let's go to that terminal and telnet localhost 3270. 3270 is just the network port number that Hercules configuration file tells the system to listen on. Don't confuse this with the fact that it's a 3270 device. We're not using a 3270 device right now. We're just using that 3215 line printer and typewriter keyboard input. Okay, so we're connected to Hercules, emulating the device on address 01F. And with that, we can IPL 150. So this is booting off of the hard drive at address 150. Okay. Let's go back to Hercules and do that. IPL 150. Okay. So our mainframe is up and running. If we go over to our console, you can see that our system is asking us to specify system parameters for release 3.7.VS2. So as described in the instructions we've been following, the starter system is actually a little MVS 3.7 system that comes prepackaged from IBM. And this is the system we're going to use to install the MVS 3.8 system onto our new empty DASD or hard drives using the distribution tapes. So in any case, back to the instructions to see what we should do next. And in this case, we are going to say reply to message 0 with the command CLPA, which rebuilds the link pack area. This is clear link pack area. Okay, so R0 CLPA. You'll notice on the MVS console, whenever we're asked a question, we reply to that question. And later in the boot process, each question will have its own number. So I can reply to question 1, I can reply to question 2, I can reply to question 3. We don't have those yet, so it's just implied that I need to reply to question 0. So this is the reply to specify system parameters for this release. Okay. So now we have another question. In this case, we do get a number, and it's 0 again. Specify options for HASP2 version JES2. So these are the JES or JES2 startup options. Let's look in the instructions. Because this is a new system, we want to format the spool, and we have, I guess, no other requests or no other requirements. I've never quite been clear on what that was short for. But essentially, we're saying we want to do a cold start of JES2. So let's put that in our operator console device here. Okay. So now, question number 1. Reply yes or no to confirm checkpoint record change. This is saying, hey, dummy, you're about to do a cold start. You could, lose some data. You could lose some recoverability if you're trying to boot back up after a system crash or something. The system's just asking us to confirm that we really want to do this. So we can reply to question 1 with the answer Y for yes. Okay, all available functions complete. So we are now booted into a working starter system. This is the MVS 3.7 starter system distributed by IBM. And we have JES 2 up and running. You can see we have some initiators that are active, and we have some job classes set up. But let's go back to the instructions. You can see it did tell us to reply yes to that checkpoint question, and we've completed initialization. Now, because we got 3 initiators, we don't want our tasks here, our system installation tasks, to run in parallel. We want one to finish, and then we want to run the next one until it finishes, and then we want to run the next one. So the instructions here are having us stop initiators 2 to 3. That will leave just initiator 1 running. This way we don't accidentally start running some of these steps in parallel. So $P is the stop command for JES 2, and then initiator 2 through 3. So we can copy that command over, enter it in our operator console here. And so we stopped those 2 initiators. Okay. So next step, we want to attach those new DASD images that we created. We did not attach them when we booted the system. Let's go back up to our diagram here. Up here, we created those 3 additional DASD, work0, work01, and SMP 000. But our configuration file for Hercules did not have them attached to the system. And the reason that we didn't want them attached to the system when we IPL'd the starter system is because they weren't yet formatted necessarily, but we also didn't want the system to just start using them as work devices. We want to set them aside for particular usages, and we want to be able to format these volumes before we mount them. And so we didn't want whatever automatic behavior MVS has for DASD that's attached that it doesn't know what to do with otherwise. So we booted the system up. We got MVS 3.7 up and running. And now we want to go to our data center, and we want to plug in and power up these 3 extra disks and connect them up to our mainframe. And so again, I think I mentioned in the last video, when we want to do something physical to our mainframe in the real world, that's when we go to the Hercules console and manipulate the mainframe itself. So in this case, there's a script provided that has the commands to attach these 3 devices. So these are essentially just the same commands you would find in the config file. We can just run them after the emulated mainframe is already up and running. So let's go back to the Hercules window. So now we're back in Hercules. We can run that script, and that has attached these 3 additional 3350 devices to our emulated mainframe. So now if we were to look at that diagram, we would see 3 extra boxes for these 3 extra DASD. You can hit escape in this Hercules window, and it gives us a kind of a graphical monitoring view of what's going on. You can see the processor registers, which could be interesting if you're building an operating system from scratch on here, just directly trying to execute some S370 instructions. You can see a little speed readout here, how many MIPS we're executing, how many IOs per second we're executing. But you can also see the device list. And here we can see that sure enough, we've now added these additional 3350 devices. So I'll hit escape again to get back to this view so that we can enter commands to Hercules, since we'll be doing a lot of that. But for now, let's go back to the instructions. So again, the instructions explain what's happening at each step. We're going to be running a lot of JCL that's creating a lot of data sets and reading the data from the tapes and just preparing the system for much of the work to come. I would encourage you, if not on your first run through of these instructions, definitely your second, to start looking at these scripts before you run them. They're not all going to make sense. To make full sense of them, you'll probably need to reference things like the SMP System Programmer's Guide. There's a lot of good old documentation for the IBM operating systems and mainframes and MVS 3.8 in particular, and other versions of MVS on the BitSavers website. So bitsavers.org. You browse their computing archive. You can go down to IBM 370. There's an OSVS2 folder with a release 3.8 folder. That's the specific release we're running. There's not always the documentation for 3.8. So you might grab some things from 3.7. It'll be pretty applicable to the 3.8 system, and so on and so forth. But in this case, they do have the system modification programmer guide for our 3.8 system. So you can start correlating some of what you're seeing in the setup JCL with some of the information that's available in this old IBM documentation on BitSavers. But again, for the most part, we're just going to be running through these steps, and I'll leave it as an exercise to the viewer to decide how in-depth you want to get into looking more and more into what's actually happening in each of these. Now, it's worth noting, because this is the first time we're going to run this kind of command, but you'll see we'll end up running it dozens of times by the time the series is over. The JCL files came from that install MVS bundle that we downloaded from Jay Mosley. And these are JCL job streams. We can pull one up and we'll see that it's JCL like you'd expect. What we're doing is feeding these into the system through the card reader. So one of the devices on our system at address 12.12 is the card reader. And in Hercules, we can say, I want you to initialize this device, device 12, with cards, with this stack of cards. And then once I have that card deck loaded, send the EOF signal to the operating system, which in this case will trigger the job entry subsystem, JES2, to execute the JCL, or queue up and execute the JCL from that card deck. So for each of those files in the JCL directory, we're eventually going to be feeding it into the card reader by using this Hercules command. All right, so let's do that for the first one. So again, we're using the Hercules window and the Hercules command prompt because putting the cards in the card reader is something physical you would do to the mainframe. So we'll dev init 12 with the SMP 4P44 JCL. And when we do that, if I switch over to our 3215 operators console, you can see that JES2 got this job on reader 1. The job has the name here. It has the job itself actually printed out that an IPL is required after this job is completed. Okay, good to know. And it is looking for some kind of device here, right? So we're back in MVS now. This is the MVS operating system. This is the MVS operators console. So it's asking us to reply with a device name to continue running this job to satisfy this criteria that the job is asking for. So back in the instructions, we need to load that tape into our tape drive. And so that's something that we do to the mainframe. So much like we used the dev init 12 command to load a deck of cards, a stack of cards into the card reader, we use the dev init command on device 170, which is our tape device, to load our product tape into that device. So let's copy that dev init command, and we're going to run that in Hercules, because again, I'm physically doing something to the mainframe. I'm putting a tape in one of the tape drives. And now that tape is loaded up into tape drive 170. Back over at our MVS operators console, and we can see this in the instructions, we need to tell it, okay, reply to message 2 and tell it that the address of the device where I loaded the tape it's waiting for is 170. Okay, that makes sense. So you can see the message number here was message 2, and it needs a reply. So I can reply to 2 with 170. I'll run that. Okay, looks like it did something. Back to our instructions. You can see now it's finished. It's dismounted the tape. And now it's asking for another tape on 170 with a different label. So in this case, because it's asking for that at 170, we are going to load the next tape it needs. In this case, the SMP4B tape. So back in the Hercules console, we are going to mount that tape in device 170. And if we look back at our MVS operators console, you can see it did a little bit more work because it already knew I want the tape at 170. I didn't have to tell it tape drive 170 again. It knew as soon as I put the tape in the drive and hit the ready to go button. But now it has some other weird message about sys1 proclib, and I need to reply U or M. So if we look at the instructions, you say we should reply with U. This all has to do with expiration dates for data sets, and it's not quite sure that I really want to replace something on the system before its expiration date has passed. We're going to see a few of these throughout the process until we get to the year 2000 compatibility support and we get all the initial base stuff loaded, and then we probably won't see them again. But for now, we just reply U whenever we're asked about this this replace data set message. So let's go back to our MVS console, reply to message 3 with U for use. And we get a message for a different data set, sys1 link lib. We will reply to message 4 with U. And we'll reply to message 5 with U. And now the message has changed. Now this job stream is running a job that is trying to initialize a volume. In fact, we can see this if we look back at the instructions. And yes, we do in fact want to initialize these volumes that we created. So we are going to reply U when it asks us about initializing the 148, 149, and 14A volumes. So let's do that. We're on message 6. We'll reply 6 U, reply 7 U, and reply 8 U. And now it will initialize all those volumes and do the rest of the work that was in the SMP4P44 JCL. Okay. All available functions complete. That's what we like to see. So now, this JCL ran a job on our system. It had several steps, and you can see it submitted more steps to do things like format those volumes. When a job runs, and let's look back at our terminal. I'm going to go over to our shell here. We have a virtual printer that's writing out to this file PRT00E. So if I look at that file, you can see that our mainframe is already creating quite a bit of printed output. And we see cover pages between the jobs, and this will give us an idea of what all is happening on our mainframe. So if I go down to the bottom and go up a bit, and this is meant for a 132 character or so wide printer, but I think this terminal only ends up being about 100 characters wide on the screen. So it doesn't quite look as nice as if you had a nice full width printer, but that's okay. You can see that at the end here, right, we had the job somewhere in here. I don't know if it's going to be worth finding it now. We'll see that each step of the job ended with a condition code. Yeah, so for example here, function created, highest condition code was 0. So the higher the condition code, the worse the error is generally how it works. You'll see things like 0 is no problem at all. 4 tends to be informational warning messages. So something didn't really go wrong, but it's something you might want to know about. For example, if you try to delete a file that isn't there, it's fine because in the end, it's the same as if you deleted the file. It's not there, but you might get a warning of severity 4 telling you, hey, you tried to delete a file, but the file was already not there. So we'll just continue on. But if you were expecting that file to be there, it's just kind of a flag to you to let you know it wasn't there. Then 8 and 12, and it goes on up, are higher and higher severity levels. So what we want to know is, did all of the steps of this job we just ran complete successfully? Now, I don't know about you, but scrolling through all that printer output would be pretty tedious trying to find all those completion codes. So that's where the condition code Perl script comes in. Remember in video 1, we made this executable, so I can just say, run the condition code script, and it takes a parameter of the printer output file and then the job name that I want to filter on. So in this case, we just ran this job called SMP4P44. The output is in our printer file. So let's pass those as parameters to our condcode script. And this script will read through the printer file, find the job SMP4P44, and it will show us the completion code for every step in that job. And in this case, they were all 0. And that's what we like to see. That's ran perfectly, not even any, non-critical warnings. So as we're looking in the instructions, for each step we run, Jay has put what we expect the condition codes to be. Because there will be steps where we expect to get that non-critical warning 4, or maybe even an 8. And so it's good to know, did something go wrong on my system, or is that expected? And we'll see on each step that we can compare our condition codes, our completion codes, to the expected completion codes. And if we start getting, 12s where we're not expecting them, we'll know that we might have done something wrong. Either a modification we made on our own broke something, or there's something else going on that we're no longer quite on the same path as the instructions here. Okay. We saw that an IPL was required after this job is completed. I believe this is because we're making modifications that need to be built back into that link pack area. So we will stop the system. We'll do a nice controlled shutdown where we stop JES2. We run the end of day procedures, and then we quiesce the system to make sure that all the disk activity is, I guess, flushed and done and ready to be turned off. So this is going to be a routine that you're going to get used to, because this is how you'll shut down your system even once it's all set up, perhaps with some extra commands to stop extra services beforehand. But ultimately, once all of the jobs on the system are done, we shut down JES2 itself with the pjes2 command. So this is a command I give to the operating system through the operator's console, pjes2. And then you'll see the next step is zeod, and then quiesce. So we can say zeod, EOD successful, and then quiesce. And we're not going to get any result back from quiesce because we've essentially just completely stopped the operating system now. If we go back to the Hercules console, we can see that that has actually signaled to the system and put the CPU in a disabled wait state. And now we're just back in a wait state in Hercules, and no instructions are executing. Okay, so that's a clean shutdown of the operating system. Now we can quit Hercules, which is the equivalent of powering down the mainframe, right? Throwing the switch to off. So now we're starting back up. Similar configuration, but this time we will pre-attach those volumes because they've now been formatted and prepared such that we're happy with the system having them available at IPL time. Otherwise, it looks like the system is pretty much the same, but there is one card that's going to be preloaded into the card reader. So the first thing, once JES2 starts up, is it's going to have a card ready for it with some JCL that's actually going to mount these volumes with the correct parameters. Okay, so we'll start up Hercules with the slightly modified configuration file. Now you'll note again, I can hit escape, and here I can see that all those drives are attached, and our card reader is sitting here with that card deck ready to go, just waiting for the operating system to try and read something from the card reader. So we'll hit escape again. I am going to reconnect my 3215 console. Again, I shut down the mainframe, so I lost that connection. So we're just going to telnet localhost 3270 again. And now we have our operator console hooked back up to our emulated mainframe. We're going to boot, so we IPL from device 150. And in this case, in fact, we don't need to rebuild the link back area. So on that specify system parameters, instead of providing a reply in R0, CLPA, we'll just hit enter. And that's the way we tell the system we don't have any particular special requests. We don't have anything we need to tell the system. Similarly, for Jez2, this doesn't have to be a cold start. We've already formatted our spool area. So the normal way you start Jez2 for a warm start is just with no rec. Again, either no requests or no requirements, whatever that means to you. It's probably in the documentation somewhere. So we're going to boot up from device 150. We'll just hit enter when MVS asks for options, and we'll do a normal warm start of Jez2. So back to Hercules, IPL 150. That gets the system going. And then over in our operators console, specify system parameters, we just hit enter. And then Jez2 startup options, we reply 0, NOREQ. Okay. Now remember I said there's a card, or a deck of cards already in the card reader, just waiting for something to read them. And sure enough, when Jez2 starts up, it attaches to that card reader, and it now has a job that it's read in. And it's apparently a job that wants us to confirm that we're about to do something. So you can see here, what we're doing is trying to mount some of the volumes, some of the DASD with the private attribute, so the system doesn't just throw random work data on them. So we will go ahead and reply, yes, we want to allow it to run the command to do that. So R1Y to execute that command. I did that. Now all available functions are complete. Okay. We can check the condition code of that mount command. I guess for completion, we'll do that this time for completeness. So I can go over to my shell, and I can run that condition code Perl script, give it the printer file, give it the job name, and we can see that sure enough, that completed successfully. All right, now we're going to, I think, just run a bunch of JCL. So the first thing is to initialize the SMP environment. Again, this is just getting some of the required data sets, deleting old data, and then creating some new empty data sets that the SMP environment needs. So we'll run that command in Hercules to load that JCL into the card reader. So over to Hercules, enter it there. You'll see as soon as that's in the card reader, if we go to our operator console, it grabbed the job, and you can see all available functions complete. So that completed quickly. And we can check for the condition codes of this SMP job 00. So let's do that. I'll just hit the up arrow here and change it to, what was that, SMP job 00. You can see it's highlighting that we have 2 completion codes other than 0. In this case, this is an example of, I guess 8 is also kind of a non-critical warning message where we tried to delete something that wasn't there. And so it's giving us that non-0 completion code. But here's where it's nice. We can check back with the instructions and see, okay, that's expected. So nothing's going wrong. And I think it'll tell here, yeah, basically initializing data sets that weren't there, trying to work with an empty data set. So this is expected and acceptable. All right, receiving the MVS product elements. So this is going to read the product elements from tape and load them into SMP data sets on our hard drives. So let's run this JCL. Again, we're putting SMP job 01 into our emulated card reader. So we do that in Hercules. And this time, when we go back to our operator console, it read in that job, and this job needs a tape. Okay, so what tape do we need? It looks like we need the product tape. We'll mount that on device 170. So that's back over in Hercules that we tell it attach this tape to this tape device. And then back over at our MVS operators console, we'll reply to message 2, telling it we've provided that tape at device 170. So R2, 170. Okay. So there's more information here if you wish to read it. And we will wait for this job to complete before we check the condition codes. So let's go back to our console. Still running here. This is when it can be fun to look back at the Hercules window and you see the number of instructions it's emulated is shooting up. If I hit escape, we can see that there is CPU activity, there's IO activity. This is essentially copying all of this data from one of these tapes to the staging area in some of our DASD. So we'll give that another minute. Look back. I'm going to hit escape again to get back to our normal window here. We can go back and watch our console. And we'll just wait for that job to complete. There we go. All available functions complete, and that job is purged. So that's our indication that that step is done, and we can now move on. So the first thing we do before we move on is we check, did that work successfully? So that was SMP job 01. So back in my shell, I'll run that condition code command again on my printer output. And we had one step there that completed successfully. Great. And we expect it to complete successfully. Jay is telling us here that we have over 40,000 lines of printer output from that job, including a summary. And this is something that's kind of interesting. These are the components of the operating system, the various products that were staged, received from that tape. So again, when you really want to get into, okay, these are the different components that make up the operating system. These are now the things we have loaded into the staging area that we'll be able to apply to our target system. So again, just interesting background and kind of the history behind that. So just like we received those product components, we now want to receive the program temporary fixes, the various patches and fixes and everything. So those are on a different tape, but we have a job here to load those. So let's go ahead and do that. So back in Hercules, I run the devinit command to put that JCL in the card reader. Now if I look at the operator console, it's telling me, hey, I'm running a new job, and this job needs a particular tape to be mounted at device 170. Okay, we can do that. The tape we want to mount is the PTF's tape. So let's copy that command, run that in Hercules. Now when we look back at the operator console, we can see that it is continuing to run that job. If we look at the Hercules activity display, you can confirm, yep, okay, my system is doing a bunch of work for me. So while we're waiting for that, it actually looks like it's done. Now it's doing 0 work. That's usually a sign that the job completed. Yep, okay. Let's go back to the instructions. Check that we got a 00 completion code for our job. So that's over in my shell window. I can run that const code script, change the job name to 02, and that ran successfully. So now we accept these elements. So this is going to be the step that actually takes those items that we staged from the tapes and essentially installs them to our system. So let's load the job that does that. Give that to Hercules. Tell it to put that in the card reader. Now, if we look over, we can see the job started. It's just working from everything that's already in our work areas on our DASD. So it's not going to need any more tapes. It's essentially just copying data from one hard drive to another now. So while we're waiting for that, I'm going to switch back over to the web browser and that SMP manual that we looked at earlier. And around page 41, this is just a very high-level overview of the SMP process, and it kind of explains why there were two steps to do this. Those first jobs were receiving the elements from tape. And so that was running the receive command of SMP, of the system modification program. Those essentially check for validity, and they load all of that data, all of those, whether they're program elements or fixes, user modifications. It loads them to essentially a holding tank, a temporary staging area that I think is called the PTS. And then they're there cataloged in the system. So the system knows that those particular products and fixes are available to it now, but it hasn't actually used them yet. And so when we're now in this apply step, this is what is taking those modifications. Now, a modification could be an entire new program in the case of this operating system we're loading, or fixes or other modifications to the operating system or programs that's already installed. And it takes them from the staging area and it actually applies them to the target system libraries. Now here, target system library are the actual files on our hard drives of this new MVS 3.8 system we're building. And then later there's this accept step, which will make those modifications permanent. Once I accept something, I'm no longer able to back out. I can no longer restore. So if I apply, say, a fix, a patch, and it turns out it doesn't work right, or it makes the situation worse, or it breaks something else, I can restore from the dlibs the version of that software, the version of that operating system library, whatever it may be, from before I applied that fix that I received. But once I'm happy that, okay, this is the new baseline, if I apply other fixes and I need to restore, I want to go back to this current baseline after I'd applied these fixes that are good. So the accept step is kind of the ultimate, you are making these changes a permanent part of your system. So that's kind of the process. So we saw that we received, and now we are directly accepting them because we don't actually have an up and running working system to apply them to. We're actually building the system, and so we're skipping to this accept phase. So again, good documentation available. This has, all the commands for the accept process and the receive process and the apply process, the restore process. It even gets into, I think, making your own modifications. It has the syntax for sysmods where you can do some patching of assembler source files and looking at the status. Lots of good stuff. But with that, our job is probably done. All available functions complete. Oh, no, we're still running job 3. So let's look at our Hercules console again. You can see, yep, it's still doing a bunch of work. Again, this is the step that is actually taking those distribution files and building them on our system so that they are available to us to use in our day-to-day operation of the system. Or building the distribution libraries, I should say, that we can then restore our system from. So it should be close to completion now. You can see, looks like on Jay Mosley's system, this took about 4 minutes. I think he was running on a local system. I'm off running in a VM, but we'll see. It should line up with approximately the same amount of time. Let's go back and see how we're doing. Back over to our operator console. Okay, so it's done. SMP job 03, all available functions complete. Let's go back to our shell and look at the output of that. So it looks like we got the completion code 0 for all of the steps except step 4, where we got a completion code of 4. And if we look at the instructions, that's exactly what we expect, having to do with some of the link edit steps being unable to complete, which is expected. All right. So if we look back, that was page 41. Yeah, 41. There's another thing you can do, which is reject particular modifications. And that will clean them back out of this holding tank area. Now, because we accepted all of these to our permanent distribution libraries, we no longer need to keep the original copies in the holding tank. I don't think the technical term is the holding tank. It's just what I like to call it. So we're going to reject those just to free up that space. And that is done in the SMP job 04. So let's give that to the Hercules console. Look back at our console here, and we can see that that happened pretty quickly. All available functions complete. SMP job 04 is purged. And in our shell, we'll check the results of that job. And you can see we got a completion code of 4. Let's look at the instructions. And sure enough, we expect a completion code of 4. So everything's good. Now we'll apply the system modification to add device support for newer DASD types, 3375, 3380, and 3390. Yeah, it's really cool we can do this. And that is provided through this job. So let's run that in our Hercules console. And if we look at our operators console now, you'll see that we need a tape J90009 on device 170. And if we look in the instructions, sure enough, that is one of the tapes that was provided to us. So we will mount that tape using the Hercules console. Now, if we look back at our operators console, it finished the job. All available functions are complete. Let's check the completion codes of job 5. And that worked perfectly with a completion code of 0. And sure enough, we can confirm we expect one step with a completion code of 0. All right, so user mods must be accepted. So now we are going to accept that user mod that we received. So again, we received it. That copies it from the tape to this holding tank area. And then if we accept it, it's going to permanently apply it to our distribution libraries on our system. So we can run this JCL. We'll provide those cards to Hercules, to the card reader. You can see this job has started. So this is now making all of those modifications to support that new those new devices, integrating them into our system distribution libraries, and all available functions are complete. So if we check the completion status for that job over in our shell, looks like we had one step with completion code 4. Let's check the instructions, and yep, that's what we expected. Same reasons as before, some of the link edit steps aren't ready to be run yet. And after accepting, we'll now reject so that we don't keep anything in the holding tank that we don't need anymore. Go back over to Hercules, run that by putting it in the card reader. And again, that was quick. All available functions complete. If we look at job 7, we have completion code of 4. And if we look at the instructions, we expected a completion code of 4. Very good. All right, so we need to rebuild the device support facility, and we need to relink the assembler to get around some problems it had. So again, this is getting into some fixes for, looks like, occasional abnormal ending codes that you might hit otherwise in system generation for unknown reasons, which is always comforting. But despite the reasons being unknown, apparently folks have figured out what the fix is. So we'll run this job, and that will apply whatever fixes are necessary here, and to get us the device support facility so we can write IPL records onto our target system residence disk. So back over to Hercules, load those cards. And on our console, it looks like we're getting these warnings about expiration date not passed on data sets that we're trying to modify or replace. So we will reply with U. Note here, there's 2 outstanding questions that need replies, both 3 and 4. So R3U and R4U. In the meantime, it looks like number 5 came up, so R5U. And with that, the job's completed. All available functions complete. Let's check the code for job 8. We got all zeros, which is always comforting. And we can see here, we had instructions to reply U to each of those, and we got those. All right, so it looks like one of the things this job does is actually automatically create and submit a job called job 9. So let's look back over at our console, our MVS console. Okay, sure enough, after job 8 finished, it submitted this job 9 automatically. So let's use our concode script to check job 9. Okay, good. Job 9 also finished as we expected with 2 steps with a 0 completion code. Now, one of these things required an IPL. So we're at the point where we can shut down our system again. So this is just the normal, or what will become normal to you if you continue using the system you're building. We can shut down JES2, and then we can cleanly shut down the rest of the system with a ZEOD and a QuiS. After that, we'll be able to quit Hercules to really power off the mainframe, and we will have built our distribution libraries. So let's go ahead and do that. Back in our operators console, we will stop JES2. Okay. We will now do ZEOD for the end of day tasks, and we will QuiS the system. Again, QuiS doesn't return anything, but if we look back at Hercules now, we can see that sure enough, the QuiS command stopped the processor, and all processing on the system has finished. So we can go ahead and quit Hercules to power off our mainframe. All right, there's some advice here to save the printer output from this step, because this is where we loaded all of those product elements and fixes into our distribution libraries. So that printer output will be our permanent record of what we actually did to this system. You can also back up your system at this point. So let's go over and look at what we have. So we have our printer output. You can see we got quite a bit of printer output. That's nearly 10 megs of text that process produced. Next time we start Hercules, it always overwrites the printer file with a new blank file. So if you do want to keep the output from the process of building the distribution libraries, you can just copy that file off to, maybe call it dlib print output.txt. Again, it's 10 megs, so you can compress it if you want, but 10 megs is 10 megs. Nobody really cares. The other thing of note is, remember, we're using these emulated hard drive files, these DASD files in the DASD directory. So you can see they all started out empty, but over the course of doing this, we restored some data to start1 and spool0 for the starter system. We've also populated the SMP volume with all of that product information from the system modification program. And it looks like it used that work volume for a lot of data sets as well. So when we move on to the next step, which is actually the system generation step, if we mess something up, we could leave our system in a state that that we don't understand, and it might be quickest to just start from scratch. Well, it'd be kind of annoying just to have to go through these rote steps of loading the data from tape, applying those fixes, and all of that. So one of the things we can do at this point is if I just back up these hard drive images, I can always start from this point, just where we left off. We haven't really done any of our own modifications or customizations to Jay Moseley's instructions up to this point, because again, this is just kind of the baseline of we need to get the actual product elements from the tape to some hard drives. So I don't really find I ever need to go back and start at an earlier point than this. So what I like to do here is just create a file. I don't really need to compress it because we're using compressed DASDs, so they probably won't compress it down that much more, at least not enough to really matter. So I'll just create a tar file. We'll call it, maybe backup post distribution libs, something that makes sense to you, kind of lines up with the step name in Jay Moseley's instructions. And all I need to back up is the DASD directory. Okay, so now I have that backup. And if I want to build another system, I can just use these as the starting DASD and pick up from the next step we're going to do, which is the system generation step. And that's where it's fun to start making customizations and everything. So it'll save you some time in the future if you just put that aside and keep it as a starting point. You could even keep that printer output as part of this archive, just so again you have all that data that if you're starting from that starting point, you have some reference information about what's in the system that we built so far. So up to you. It's convenient. I have found that making mistakes in these next few steps gets me in a state I don't really understand. So it's easy just to restore the DASD images and try again and figure out what I might have done that caused my system to go bad. So something I recommend doing, and easy enough to then just untar those guys and replace the DASD, and you're at a good clean starting point again. All right, with that rambling out of the way, we are now ready to perform a system generation. So in the next video part, we will pick up with those next steps. Thanks for watching, and we'll see you again very soon.